Hello. So today I'm going to talk on solid mechanics. So in that one, it is a part of a strength of material. In that one, I want to discuss today bending moment and shear force diagram for determined structures. Okay. So there are a lot of syllabus will be there. Today I'm going to cover only on the bending moment and shear force in statically determined beams. So in the subsequent lectures, I will cover simple stresses and their relations, simple bending theory, flexural and shear stresses, shear center, uniform torsion, transmission of stresses, buckling of columns, combined and direct bending stresses, etc. So today we'll see what is different types of beams. So if you have a determined beams, simply supported beam, overhanging beam, cantilever beam, and indeterminate beams are fixed beams, continuous beams, proper cantilever, etc. So you should know what is a moment. It is a product of force and perpendicular distance between the line of action of the force and the point about which the moment is required to be calculated. And also bending moment. The moment which causes the bending effect on the beam is called the bending moment. It is generally denoted by M or BM. So sign convention, if you already know, the sagging bending moment is considered as positive. That is the convexity at the bottom. So that is considered as the positive. And similarly, if you have the negative bending moment, that is a hogging moment. So it will be similar to this one. Convexity, it will come in the top. So similarly, the sign conventions for different things, I think I want to tell. The bending shear force will be, if we have a section, if we take at the section, left side, if it is acting upward, it is positive, and from the section right side, it is a negative. And similarly, if it is in the other side, so that is a shear force acting upward from the section and downward in the right section, it is positive, and from the section it is acting downward, and from the section it is acting upward, it is negative. So the shear force and bending moment diagram for a different thing. So if we consider the diagram which shows the variation of shear force along the length of the beam is called the shear force diagram. So that is called SFT. Bending moment. The diagram which shows the variation of bending moment along the length of the beam is called the bending moment. So you should know what is the point of control flexure. So it is the point of bending moment diagram where the bending moment changes its sign from positive to negative or vice versa. It's called the point of control flexure. So it is also called as a inflection point. At the point of inflection or control flexure, the bending moment is zero. So that is the point of control flexure. So we'll see what is the relation between the moment and shear force and the loading. So if we consider a beam, it is subjected with a simply supported beam. We have a hinged condition and a roller condition at the end, and it will be having the arbitrary load as shown in the figure. So take a section x and x dash, x1, x dash and x dash. So it will be the simply supported beam subjected to general loading. So consider the differential element. So this is called the differential element. So it will be considering from x2, xx and x1, x dash is shown in the figure. So we'll be having at a small element if you take, that is a distance dx. So it will be having the v is here, and the other side v plus dy, and the moment m will be there in the left side, and the right side will be m plus dm. So this is the loading what you wanted is interested. So loading will be a kilonewton per meter. It will be there as it is. So considering the moment at the point O. So these are the forces, that free body diagram. If you consider, these are the forces acting. That means shear force, moment, and the loading. So if you take the moment at O, what are the forces acting? Moment M, it will be there. m moment, m plus dm, so other side. So taking a clockwise direction as a positive, m plus dm is a positive, minus m is the negative, and v into dx, that is the moment taking here, v into dx, and other side v plus dy, if you take in the moment at o, so that has become 0, and we have the arbitrary loading for a distance of dx. So w into dx is the total load. So acting at a distance d by 2. So this is the equation of this one. So if you neglecting the small quantity of higher order, then we'll be getting, only thing we will be getting this one, v into dx is equal to dm. So we can say v is equal to dm divided by dx. That is the differential of moment with respect to x. So shear force will be differential of moment with respect to x. Similarly, if you take free body diagram of the differential element, same, all the forces will be there. So if we consider the equilibrium equation, that means sigma Fy is equal to 0, then we'll be considering as V in the positive, that is acting downward is negative, V plus dy is a positive, and W into dx is the total load. So we'll be getting dV is equal to W into dx. So that is load, whatever considering is equal to differential of, that is the differentiation of shear force with respect to x, will be getting the load. So this is the relation between the intensity of load and the shear force. So the variation, if you see, the variation of shear force and the bending moment for various standard loading as given below. So if you consider, the type of load will be there, and the shear force or bending moment in the other column. So between the points of loads are the no load region. So if you have the shear force, what you will be having only horizontal line. If we have a uniformly distributed load, we will be getting the inclined line. Okay. So uniformly varying load, it will be having the 2 degree curve, that is a parabola. So bending moment, what will happen? So it will be for the load, no load region, it will be inclination. So that if you have a uniformly distributed load, 2 degree curve it will be there. Similarly, if you have the uniformly varying load, it will be cubic curve. Okay. So this is the some fundamental you should know, and so we'll consider some problems how to draw the shear force diagram and bending moment diagram for a simply supported, similar to like this. So it is very simple. It is a, we'll take a simple problem. So we will be having the different load on the beam. So it will be having one end, it will be hinged support, and other will be roller support. What you have to do, first step is equal to, so we have to calculate the reactions. So we have to calculate the reaction RA and RB. So if you want to calculate the reaction at RB, so RB, you take the moment, that is moment sigma MA is equal to 0. Considering all the clockwise moment is equal to positive, so we'll be having RB into 8, and all the loads into distance will be considering, and we'll be getting the RA in the upward direction, that is RB is equal to 13.25 Newton. So if you take the summation of all the forces, the vertical forces, we can calculate the force RA is equal to 7.95 Newton. So once if you know the reactions, so we need to calculate the shear force calculation. So for example, if you want to calculate the shear forces at section 1.1, here you see this is the section 1.1. So denoted by V11. So what will happen? Left side from the section, whatever forces are there on the left side of that force, it is considered as the shear force. For example, here V00, there are no other forces. So that is why shear force will be 0. So V11, so we have only reaction. That is 9.775 Newton will be there. So similarly, you can consider that 2233 like that. So what will happen? 22. So it will be again left side of this load. So you'll be having only reaction. So that's why you will be having only reaction of that one RA. So similarly, if you take at 3.3, so you'll be considering, so this is positive. It is acting upward. The reaction is acting upward. that will be, that's why it is positive, and this force acting, it will be downward, it is negative. So resultant will be 4.75. So similarly, we can calculate other points for VV44, VV55. So shear force at 66, shear force at 77. So finally, we can draw the shear force similar to this one. So you'll be having all the forces after calculating. We'll be getting all the above the, this is the baseline. Above the baseline, whatever forces you are drawn, shear forces, it will be positive, and below the baseline, it will be negative. So you can draw like this. So you should get whatever reaction, if you see in the previous section. So reaction will be 13.25 will be there. That is, we got here 0. So that is the check you have to do at the end. You should get 0. So you can see here. So this is the shear force diagram. So now let us see how to calculate the bending moment. So bending moment usually at the simply supported roller end moment, it will be 0. So if we bending moment, similarly, what you have to do, so you have to calculate MA is equal to 0 since it is simply supported. That's okay. So you need to calculate MC. So moment will be, so either you can take a left side or right side of the section. So you are interested to calculate the moment at MC. So what will happen? MC is equal to reaction into perpendicular distance. That is the one, it will be there here. So that is the next MD. MD, either you can take right side or left side, it doesn't matter. You see that one, which is the smallest number of reactions will be there, that will be have to be considered. So here 9.74 into distance. The distance will be varying. So initially we have taken is equal to 2 meter. Here it is become 4 meter. Okay. So 5 into 2 is the distance. It will be 5 into 2. It is negative because it is acting in the reverse direction. So that is, we will be getting Newton meter. So moment you have to write. And ME, either you can take either right side, left side, because the right side if you take is only easy, that is reaction into, and the distance you can measure, that you will be getting the same thing, 13.25 into 1, you will be getting the moment. So either you can go either left side or right side. So these are the moments. So finally we should get MB is equal to 0. So it is also simply supported roller endpoint. So okay. So what you have to do, you have to, on the baseline you have to take, and that one you have to draw the, all these are sagging moment. So that way it will be positive. So we will be drawing all the things, it will be positive. Okay. So we will take another example on a cantilever beam. It will be subjected to UDL and also an inclined load at an lever arm given like this. That is a 0.7 and 0.7 meter and 0.5 meter will be there. So what you have to do, here you have to resolve the forces. So for example, here the UDL is okay, no problem. It is vertically downward. So you have the inclined forces at degree 30 degree, it will be there. So you have to resolve that forces. So what you have to do, 40 cos theta will be in the horizontal direction and 40 sin theta will be in the vertical direction. So once if you resolve, you have to come all the forces you have to transfer to the this on the beam. So how to transfer? So this is the vertical force will be there. Vertical force, it will be coming directly vertical forces, and this moment will be there. That moment will be coming at this point. If you take that vertical force acting downward and moment acting this-ward because of this vertical force, that is 20 kilonewton. So another force will be acting, that is 40 cos theta. It will be acting at a distance of 0.7 meter. That moment will be acting in anti-clockwise direction. That moment also you have to consider here. So resultant moment, this one moment will be clockwise, another moment will be anti-clockwise. So you need to consider the resultant, which is the maximum. So that you have to put there. So for example, here you see, so this is the resultant moment you are getting. So both if you take, so moment, whatever force, vertical forces transferred here and horizontal forces are transferred here, and the result moment will be, it will be acting in the anti-clockwise direction. So what you have to do, you have to calculate the reaction. Next, for drawing shear force or bending moment diagram, you have to need to calculate the reaction. First, you see that one. So sigma Fx is equal to 0. So that is a horizontal force. We are not interested in the horizontal force. because that shear force diagram will be only for the vertical forces in this case. So we will take here, and sigma Fy is equal to Vd, that is what is the reaction? Reaction will be, so 20 into 3, that is the vertical force, 20 into 3 it will be there, and this vertical force 20. So totally 80 kilonewton will be getting the reaction at Vd. So moment, if you see the moment, so you have to calculate the moment. Md is equal to, so whatever the forces acting here, so force will be acting at the centroid of this one. So 20 into 3, it will be acting at a distance from here to here. That is how to calculate. So 20 into 3 will be there, and this is the 1.5. So you are interested to calculate MD it will be there. So you have to calculate here 1.5 plus 1 plus 1, that is 3.5 to be there, and this is 20 into 1. So this moment you have to take as it is, whether it is a clockwise direction or anti-clockwise direction. These are all this acting anti-clockwise. This also acting anti-clockwise from this point. So this also acting in the anti-clockwise, the moment also. So all the things will become negative. So this is the force. So negative force is acting here. So negative moment will be there. So this is the shear force. Shear force at 1, there is no other force left side of that one, that will be 0. Okay. So if you take the V22 at the point here, what are the forces acting? That is a 20 into 3, that is 60 kilonewton, it will be there. Okay. So the shear force at 22 will be 60 kilonewton. So similarly, if you take at 3, so left side of the 3 will be to consider. So that will be only 60 kilonewton in the negative direction, because from the section it is acting downward, so it will be negative. So if you consider 4, so it will be 60, whatever 60 is there from here, it will be transferring here, and this is the force acting here, 20 kilonewton acting downward again. So you will get 80 kilonewton. And at 5, if you come to at 5, all forces left side of the section have to take, that is only 80 kilonewton will be there. So we are getting 80 kilonewton, that reaction, so we will be getting 0. That is the check you have to do. So finally we should get 0. So bending moment, so loading diagram, you will see that one. This is a shear diagram. So all the things, it will be negative direction. So this is, so we got 60, that same thing. So there is no force acting in this one. That will be, that's why it's horizontal, and this is the vertical force acting downward, and it will be coming here, and it's coming up 80 kilonewton. So okay. So this is a shear force diagram, and the bending moment diagram, it will be, so MA at the end, it will be, a moment will be 0, and MB whatever load acting at left side of the section. So 20 into 3 into 1.5, that is the acting anti-clockwise direction, is negative. So 98 will be there, minus 90 kilonewton meter. So MC, moment at MC is equal to 20 into 3 into 2.5. So the distance from here center to the distance you have to calculate here to here. So to 1.5 plus 1, that is the 2.5 will be there. That is the moment at that point. And the MC of this one, it will be calculating, it will be 20 into kilonewton after the MC, and the right side of the section, it will be the moment also have to consider. So okay. So that's considering the moment also. So finally what will happen, MD is equal to, you'll be getting what our total moment from this section. So you have to calculate all the things. So distance into force, all the things will be there. That is the maximum 244.25 it will be coming. So moment will be there. So MD it will be, so finally we'll be getting 0. So loading diagram, if you see, this is the loading diagram, this is the bending moment diagram. So it's the bending moment at the free end, it will be 0, always it will be 0. And unless otherwise, if you have a moment at that point, it will be different. So if you have a all concentrated load or a UDL, it will be 0. So moment calculated B, MB, and MC, it will be there. And so because of moment, it will be vertical drop will be there. That is the, so you should remember, if you have a moment at the any section, it will be having the bending moment at vertically down. So that is the one, and here will be having the moment. Okay, that's clear. This is the bending moment diagram for cantilever. So we have worked out one simply supported, one cantilever. So we'll go some examples taken from the previous gate question papers. So this is the one question paper. It's a frame A B C D. So A B C D to be there. So supported on the roller at A and hinge at C as shown in the figure. There is a hinge will be there and roller will be there. So now what they are asking, so the reaction at the roller end, what is the reaction at the roller end? So what you have to do, you have to see there is no horizontal force. So we have only vertical force here P and here also vertical force P. And if we have any horizontal force, then only it will come into picture for the roller. So there is no horizontal force. So that's why what will happen? The reaction at the roller point, what will happen? So they're given the option like this. So A, is it a P or B, 2P or P by 2 or 0? So what will happen? Because there is no horizontal force acting on the member, either member AB or BC or CD, so it will become 0. So solution will be 0. Just see that one, that solution is a D. So this is clear. So this is the one having a hinge and a roller here. So they are asking what is the reaction at the roller end. So that means reaction, it will be having only reaction perpendicular to this one. So if we have any horizontal force, that will be coming to picture here. So now we will consider the three prismatic beam with the clamped support PQR as shown in the figure. PQR, it will be there as shown in the figure. Given that modulus of velocity is equal to 2.5 into 10 to the power of 4 MPa, and the moment of inertia I is equal to 8 into 10 to the power of 8 millimeter to the power of 4. The correct comparison of magnitudes of shear force and the bending moment developed at the support. So this is support. What they given was P support. It will be all our cantilever beams. First cantilever having only vertical load. So now we see there is what is the shear force. Shear force, it will be constant throughout this one. So that is the shear force. So that will be there. Like this is the shear force. So what will happen for the UDL at the end? It will be 0. So this is because moment is there. Whenever acting moment at any point of the beam, so shear force will be 0. This is the one. So what will happen moment if you see moment, then depending moment will be looking like this. So what happened? First one, it will be having the section here 80 into 8. That is the moment acting at the fixed end. So here 20 into 8 at a distance at 4. That is also 640 will be coming. So here 640 Newton meter given exactly. Now we have to compare. They are given 4 options. So you have to see which option is correct. So shear S means shear force at PQR and moments PQR will be there. So we have to compare one by one. So you see here, so shear force at P, is it less than Q? Of course, it is less than Q, but it is not less than R. So that is wrong. It is gone. This will not. So one by one you have to come. So shear force at P is equal to Q ಅಂತ ಹೇಳ್ತಾರೆ. No, that is not the correct. So shear force at P is less than Q but greater than R. That is first condition. Okay. And the moment at P, moment at Q, moment at R. So that is correct. So this option, C option, is the correct. So once if you compare all the values, so we will be getting that one. So what is the result? So result will be option C is the correct one. So we'll see next one. A beam having a double cantilever like this attached at the midspan as shown in the figure. The nature of force in the beam, this is the beam AB. What is the nature of force in the beam? We are interested to know what is the nature of force in the beam AB. So length they are given, all the lengths length AC is equal to length AC is equal to CB. So whatever length this one is equal to this one, and this length is equal to this length is equal to this length, they are given. So although also they are given the force P is equal to P. So they want to know what is the nature of force, whether it is a bending or shear, or bending, shear, and torsion. So whenever you is acting a force, that force can be transferred on the beam with a force and a moment. So force, acting a force and a moment, you can transfer these forces. So finally, what will be it will become? It is a simply supported beam having a constant load and a moment. So that means it will be having only two bending moment and shear. It will be governing. Okay. So that is the thing. So we'll see that one: bending, shear, torsion. There is no question of torsion. Only bending and shear. That's okay. There is no torsion, and torsion and shear, that is not correct. So whatever load is acting at the elevated portion like this, so that can be transferred to the exact beam by the force acting on that one and the lever arm. Whatever lever arm acting here, that can be transferred here to as a moment. So that finally what will get? So this will be nature of force will be bending moment and shear only. Okay. So bending moment in kilonewton at the midpoint of a location X in the beam with the overhang shown in the figure is equal to dash there. So this is the beam. So they are giving the overhang from this point. Is the overhang is a 10 kilonewton, here 20 kilonewton, here injured portion is there, and you have a spring point here. So they want to know what is the bending moment at the location of this X. So midspan location. So overhang will be there. Bending moment at X, they want to know. How to calculate that one? So we need to calculate the reactions RA, RB, and the moment you have to calculate. So how we can do this one? This can be split into, so that options they are giving here, we have to select from that one. So this is the one. So whatever force acting here, force will be there, this force will be there. So this is the, you can split this one. So RB acting here and RB acting here on the spring. So we can take the free body diagram. Once if you take the free body diagram, we can calculate RA, RB. Okay, clear? So once how we can calculate? So taking the moment at A and RA into the distance is equal to 2 meter, it will be there. And this force and this force also, this will be acting in the anti-clockwise direction here. So this will be acting the RB also in this direction. Only thing 10 into this one will be acting this one. So calculate. Once if you know RB and RA, you can calculate. So once if you know all the values RA and RB, bending moment can be calculated as this point. Once if you know either left side or right side, so 20 into 2 meter minus 25 into 1. So that will be getting 15 Newton meter. Okay. So that is option C is the correct. So this is clear. What you have done here? Only thing we have taken the free body diagram. So AB, so we will be getting the reactions RA and RB. You can calculate by taking the moment at A or B, and we can calculate the other reaction by taking the summation of all the forces. So equilibrium equations sigma m is equal to 0 and sigma v is equal to 0 will be solving to get the reactions. So once if you know the reactions, we are interested to know what is the moment at X. So we can calculate that one, that is the value. So here you see the focal frame shown in the figure is subjected to uniformly vertical load of W unit per length. The bending moment in the beam at a point Q. What is the bending moment they're asking here? So how you can calculate? So you can, if you have a fixed end here, it is different. So we have the hinge condition here and roller condition here. So once if you have the roller, there is no moment here. So once if you have the hinged portion, so only vertical portion will be there. Vertical and horizontal you can have. There is no moment. Once if there is no moment, you cannot transfer the moment here. So what will happen? This will be acting as a, again, simply supported beam. So what are the things you can say? Whether it is 0 or WL square by 24 or WL square by 12 or WL square by 8. So how we can write? So once if you know the conditions, what are the fixed and conditions at P and S, so we can decide whether Q and R, it will be subjected to moment or not. So once if you know that one, so whatever it will happen, it will be, so moment will be at Q. They are asking the bending moment in the beam at the joint Q. So what will happen? It will become 0. So okay. So this is the one, I will get the answer. So we'll see next problem. So we'll be having a beam like this. So that one horizontal beam ABC will be there. ABC as shown in the figure. The distance of the point of contact fracture from the end A in meter is given by. We wanted to calculate what is the distance of point of contact fracture from point A. So somewhere it will be there here, that point of contact fracture. We wanted to calculate that one. So this is the loading on this beam. So what you have to calculate? You have to. So this is the beam. So you can calculate here, or A joint, B joint will be there, C joint will be there. So reaction RB is there. So in this one can be splitted into, so 0.75 it will be there as it is. So whatever you are having here, so that is force acting in the cantilever portion. So 10 kilonewton will be there. That can be transferred to this point. So load and a moment. So load 10 kilonewton and a moment. So that is the, you can remove this one, a cantilever. Okay. So this will be acting as a cantilever one. So compatibility condition what? So if you have a simply supported hinged roller condition here, so we have the compatibility condition delta B at A, B, that is deflection at B, it should be 0. So this can be considered as a cantilever beam subjected to vertical load here and a moment here, and also reaction RB. So we need to calculate RB. So once if you know RB, then we can calculate what is the point of contact fracture. The concentric load 10 for the first one, and for the moment and the reaction RB. So once if you know all the things, you can calculate, you can solve this equation. By solving this one equation, you can get RB. RB is equal to 15 kilonewton. Once if you know the RB, so we need to calculate what is the, where is the bending moment? Bending moment 0 in this beam. So you can take a 10 into x. What is the distance? So we don't know that distance x is equal to. So at a distance it will be x, it will be there. What you are shown here, this is the distance from here, total from here to here. So that is the distance x. So 10 into x it will be there. Okay. So RB we calculated here, and we have the, there is no moment. You can take as it is 10 into x. 10 into x minus 15 into 0.25. That is the reaction. So into x minus 0.25. So this is the distance you have taken from here to here, x. This from here to here is 0.25. Why 0.25? This is 0.25 will be there. So all the things you have to calculate, because 1 meter they are given. Here 0.75 they are given. Remaining length will be 0.25. That is the thing. X minus 0.25 will be getting this distance. So that is the thing. Mx is equal to, so calculated here. So once if you know x, so we are calculating the distance x from the other end. So okay. So that is the point of contact fracture from the end A. That is the 0.25 meter will be there. So, so we'll take another problem. So here what will happen? The bending moment diagram for a beam is given. This is a bending moment diagram. So we are interested to calculate shear force at the section AA and BB. So this is the bending moment, and which beam you can see this the bending moment like this. So they're given different options and all. So we should know what type of beam. So they're given only bending moment. So at the end also you have the moment. So it is not a simply supported point. Here also moment is there. This is not a simply hinged or roller point. So that means one end may be fixed. So another end also fixed, or it may be having some movement. So what they are given here, they are given bending moment. So bending moment is there here, and this is the fixed point. So from here to here, constant moment, and here changing here inclined portion. So that is the thing we have wanted to interested to calculate. So once if you have a constant moment, we know that one, that shear force is equal to 0. And here if you see here 100 to 20, so that is inclined, it will be having a UDL. So that is the thing, and if you can calculate as, so 200 minus 100 for a length of 2 meter. So 100 divided by 2 is equal to 50. 50 point will be coming at that point. So our option C will be the correct. Shear force will be, so at that point it will be 50 kilonewton will be there. So okay, that we'll see that other one. So group 1 shows the different load acting on the beam, and group 2 shows the different bending moment distribution. So match the load with the corresponding bending moment diagram. So this is the have the moment here. So we have to match each and one. Here the only constant load at the middle point. So we have to see which is the moment is matching here. Q maybe 4, it is you know that one, and for this one also you know this one. And moment if is there, for moment it will be there here. For this one it will be there, and this one it will be here, and this is the one here. So we'll see which option is matching that. So they given PQRS will be there, and which one will be matching. So P is equal to matching with 4. So that P is equal to 4. So any other thing is not there. So we can conclude A is the correct one. Sorry, D is the correct one. So P is the D. D2 is here. So moment, sorry, P is the one. It will be having a moment here. Moment will be connected with the 2. So that is the one here. So 2 are there. You have to check once again. So Q is the constant load. It will be having 4. So that will be 4 will be there. And R is equal to UDL. So it will be having the 1. So uniformly distributed load, it will be 3. So option 3 and D is the correct one. Beam and list 2 with the diagram, that is the shear force diagram will be there, and the moment is the loading diagrams. So we have to match which is the correct one. So we can see here A will be having the full overhanging beam, and it will be having the shear force diagram, inclined shear force diagram, and I think this is the one correct one. So for this one it will be there here, and you can see the different options here. So given, and here only we have the end point. So it is only having a here shear force it will be there here. So you can see this one. So inclined force will be there. That is the one. And here you have the middle also, it will be there. So this is the portion here. And here I have the overhanging one. This is the one. So this see the option. So A is the correct option. So D is the one coming here. So we'll be getting that one. So for a simply supported of length, so you'll be having the uniformly moment m kilonewton per meter length as shown in the figure. The bending moment at the midpoint will be, so what you have to do, so they are having the similar to UDL, they have the moment on the beam. So moment will be acting, that is m kilonewton per meter length. So you have to calculate the reactions at the right hand support. VR is equal to upward, and taking the moment. So VR is, so all the moment will be there. M into L, that is the total moment, into L will be there, and VR, so reaction at the right hand, and into L. So VR will be getting M. So once if you know the VRL, so thus the reaction at the left hand is equal to VL. So will be equal to downward here. If it is upward here, so this will be downward. So moment at the midpoint M into L minus M into L by 2 plus M by 2 is equal to, at the center point will be 0. So option will be, so that is A is the correct answer. So we'll see another problem. The statement is looks like this one. The slope, so you should know the following statement are related to the bending of beams. The slope of the bending moment diagram is equal to the shear force. That is the correct one. So we'll see that one, which is the, what is the, asking the false statement, which is the false statement. The slope of the shear force diagram is equal to the load intensity. That also correct. The slope of the curvature is equal to the flexure rotation. That we have doubt, we'll see. The second derivative of the deflection is the curvature. So third one is the, this is also correct. So flexure rotation is not there. So false statement will be third one. So similarly, we will take this one. The simply supported beam will be there. AB has the bending moment diagram as shown in the figure. So the beam is possibly under the action of the following loads. So what are the following loads? It may be having the couples at M at C and 2M at D, or it may be couple at 2M at C and M at D. So what you have to do? So all the things, the different options are there given. So we have to calculate the beam. So considering that one different beam, so they given moment here and a moment at here. So we need to calculate the reactions at A and B. And once if we know the reaction, so this is the moment acting here. So moment at C is equal to only M. At D, it will be 2M. So that is the one it will be coming. So we'll see, this is the one, another problem. Simply supported beam at both ends, simply supported, loaded as shown below. The maximum moment, they're asking the maximum moment in Newton meter. So what is the, when it will be coming the maximum moment? At the center of the beam. So they're asking in Newton meter, they're asking. So they're given the load here. Once if you go give the load, you can transfer the load here directly, and also moment. So you can transfer the load here, and a clockwise moment will be there. So once if you know the beam, so it will be simply supported beam. You can calculate the reactions. Once if we calculate the reaction, and the moment will be maximum at this point only. So that you can calculate. So they are given the different options. You can calculate and simplify that one. You will be getting, this is the force. So B is the correct force. So only thing RA, RB, AB it will be there. So you have to calculate the reactions. Once if you know the reaction, from this end you calculate the moment and convert all the things into meter. So they wanted Newton meter. So that is the one. Okay. So B option is the correct answer. So for the sorry. So here loaded cantilever beam of a uniform cross section, the bending moment you wanted to know in Newton millimeter along the length mx is equal to 5x square plus 10x, where x is the distance in millimeter measured from the free end of the beam. The magnitude of the shear force in the cross section at a distance x. So what they given? So they given the moment. Once if you know the moment is equal to 5x square minus plus the 10x. So what is the shear force? Shear force, if you first derivative of a moment will be the your shear force. So derivative will be equal to 2 into 5x. So plus the 10. So that will be the shear force. What they are asking at x is equal to 10. 10 into 2.5, 25 plus the, so at a millimeter they're asking. So value will be 110 will be getting. So into, this is into, not 0.5. So 10 into 5 into 2, 10 into 10, 100 plus 10. So 110 will be there. That value will be getting at the point. So here the given is the cantilever beam. So carries the anti-symmetric load shown in the figure, where W0 is the peak intensity of the distribution load. Qualitatively, the correct bending moment of this diagram. So here the uniformly distributed load will be there. So here you can see it will be acting upward, and here acting downward. So which one is coming? It is a cantilever beam. So cantilever beam at moment at B is equal to 0. See all the moment at the B point all are 0, but it will be having upward load here. Once if we have the upward load, it will be sagging will be there, and other will be hogging. So this is the correct one. So this is the correct one. That option will be correct. This is not the correct. So it will be hogging both. You should combine hogging and sagging. Both will be there. So we'll see another problem. So here A constant at a load P act on the simply supported beam of span L at a distance L by 3 of from the left hand. So what they're given, the simply supported they're given. So they simply supported they're given. So you have to put sorry. So simply supported, and you have to calculate the forces at a distance L by 3. So it is acting at a distance L by 3 from here. So this is L by 3. So you have to calculate the reaction, the bending moment at the point of application. So you wanted to know what is the moment here. So how it will get? So you should know the reaction. You can calculate reaction at A and B. So this is the force acting at P at a distance L by 3. Calculate the reactions and calculate the moment at this point. So you'll be getting, this is the 2PL by 9. You'll be getting the value. So simply support beam with end support bending moment will be maximum. So usually on the supports, always at the midpoint, where there is no shear force, where the deflection is maximum. So what they're asking, for a simply supported beam on two end support, the bending moment is maximum. So where the shear force 0, the bending moment is equal to 0. Okay, so that is the one. So C is the answer. So we take another example. Which one of the following statement is not correct regarding the relationship between the bending moment and shear force and applied load? So you can see here the rate of change of shear force along the beam is equal to the distributed load. Okay. The rate of change of bending moment along the beam is equal to the shear force. That also okay. Rate of change of bending moment along the beam is equal to the distributed load. That is not correct. The shear force diagram and bending moment at the free end always 0. This is also correct. This is also correct. This is also correct. And none of this one. So answer will be C. So the cantilever beam shown here. So OP. So whatever the cantilever beam OP will be there. So is connected by another beam PQ. So we wanted to calculate as shown in the figure. So load is acting at P. So once if you know the load, this will be no, it's not transferring here. So you have to calculate the reaction. So whatever reaction is coming, you will take this one as a cantilever. So we will be getting the bending moment at P. Okay. So it will be 10. So today we will stop that one. Thank you very much. We'll continue in the next lecture, other chapters. Thank you very much. Okay, bye.